Hello everyone, welcome. This educational channel expounds topics in mathematics, civil engineering, and professional education subjects. This channel aims to simplify the lessons, and I am its founder, Bert, a Filipino licensed teacher and engineer. Thank you for watching.
Hello everyone. I will discuss exact equations. This topic will be discussed in two videos, and this is the first video. As shown in the list, our topic is the third lesson in the solution of some first-order differential equation. To understand our lesson, you should have a good background on separation of variables and equations with homogeneous coefficients. If you did not yet study these topics, you may spend time watching our videos on these topics. It is very clear that integration is a reverse process of differentiations. To illustrate this, we have our examples. In the first column, we are going to differentiate the terms, and in the second column, we are going to integrate. Example 1, 2x plus 3. If we are going to differentiate this expression, then derivative or differential of 2x is 2dx, then differential of 3 is 0. So our answer is 2dx. Then, this answer 2dx is now the given on our second column. We are going to integrate this term, expecting that the answer will go back to the given in differentiation. So integrate the 2dx, and the answer for this is 2. Integral of dx is x. Then write the constant c, in which the constant c here represent the constant 3 in the left side. So, as shown, integration and differentiations are a reverse process. In our example 2, we have x squared y. Now, let's get the differential of this term. For the x squared y, we are going to use the product formula. That is x squared, or differential of y, is dy, plus y, differential of the x squared, is 2x dx. Simplify, we have here x squared dy plus 2xy dx. This is the differential of the given term. Then the question, how about if we are going to integrate this x squared dy plus 2xy dx, which is the answer in the first column. So to integrate this one, that is x squared dy plus 2xy dx. This is now, it will take us a time to get here the solution. But actually, if we just know that this is an exact expressions in which the answer for this is simply x squared y, the solution here becomes very easy. So our topic here is the exact equations. For our lesson on exact differential equation, our learning outcomes are: at the end of the lesson, the students will be able to identify an exact differential equation. Second, find the solution of exact differential equation. Here is the definitions of exact differential equations. A differential equation of the form mxy dx plus nxy dy equals 0 is exact if the partial derivative of m with respect to y equals to the partial derivative of n with respect to x. In this definition, we have two important things to note. First, our dx term and our dy terms are both on one side. They are both on one side when we determine the value of m and n. We should take note for this because when n is in the other side, then the sign here will be changed. That would be negative. And the sign is very important because we are going to get the derivative of both m and n, and we are going to equate. So the equality will be affected if m and n are not both on one side. The second thing that we have to take note, our m here is with respect to y, and our n here is with respect to x. So that means you are going to get the partial derivative of this m with respect to y, and get the partial derivative of this n with respect to x. We have here our example. Is the differential equation below an exact? The equation here is 2x plus y dx plus x plus 2y dy equals 0. Our value for m here is now the algebra expressions with the dx. So that is 2x plus y. Then, our value for n is x plus 2y. We will just simply get the partial derivative of m with respect to y. That means we are going to take note only that y is a variable and the other variable x is assumed as constant. So the partial derivative here for the 2x is 0 because this is constant as assumed. Then the partial derivative of y here is 1. For our n, the partial derivative of n with respect to x, this time we are going to assume y as constant. So this is actually 0 in its derivative. And the derivative for x is 1. So as noticed, the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, in which both are equal to 1. Therefore, this equation is exact. Now let's take another example. In our another example, is the differential equation below an exact? That is 3x squared plus y dx is equal to x minus 1 dy. As I have mentioned, all the dx and the dy terms should be on one side. So we are going to transpose dy on the left side, which is the typical place for the two terms. I'm now going to write here the 3x squared plus y dx, then minus the x minus 1 dy equals to 0. In this case, our m is now the expressions in dx term, that is 3x squared plus y. Then our n is negative x minus 1. We are now going to get again the partial derivative of this m with respect to y. So again, the 3x squared is assumed as constant, so that is 0. Then derivative for 1, y is 1. For our n, the partial derivative of n with respect to x is now equivalent to, maybe for easier, we are going here to expand. So this is negative x plus 1. As noticed, the derivative here for negative x is negative 1. Then for the constant 1, that is 0. Therefore, our partial derivative of n with respect to y is not equal to our partial derivative of n with respect to x. Therefore, this is not exact. I have to emphasize that if we did not transpose this dy term on the left side, This sign here is positive. So therefore, our partial derivative of n with respect to x is also a positive, and we may conclude that both the partial derivative of n and the partial derivative of n are equal, and we may get mistake to say that our given equation is exact. As a reminder, we should always place our dx and the dy terms on one side. You can place it in the left side or on the right side, as long as the two should be on one side. Let us have another example. Which of the 5 differential equations are exact? For our solution, the steps are shown in the table. As can be seen, we will identify first the value of m and n in the differential equations. Next, obtain the partial derivatives of m with respect to y and the partial derivative of n with respect to x. Then, compare the two partial derivatives. If they are equal, then the differential equation is exact. Otherwise, not exact. Let us try our first given differential equation. 2x minus y dx minus x dy equals to 0. Here, the value of m is 2x minus y. Then, in the dy terms, the value of n is negative x. Next, obtain the partial derivative of m with respect to y. In other words, we are going to find the derivative for this 2x minus y, in which y is the variable and x is assumed as constant. So, the derivative here is negative 1. This is the derivative of negative y. And take note, the derivative for 2x is 0, since x is assumed as constant. Then, obtain the partial derivative of n with respect to x. Our n is negative x. And take note, this is with respect to x, meaning our x is now the variable and y is assumed here as constant. And derivative for this is negative 1. Since the two partial derivatives are equal, therefore, our first differential equation is exact. Our second differential equation is 2y minus 3x dy plus 2x minus 3y dx equal to 0. As can be seen, our dy term is the first term, and this is not the standard form. So we are going to convert this equation into a standard form by writing first the dx term. We have here the 2x minus 3y dx plus 2y minus 3x dy is equal to 0. This is very important to write the equation into standard form such that we will not be confused about the value of m and n from this equation. So from here, this is our value for m, that is 2x minus 3y. Then, the second term contains our value for n, that is 2y minus 3x. Then get now the partial derivative of m with respect to y. Again, y is our variable and x is assumed as constant. So again, this is 0. And derivative for negative 3y is negative 3. Then, get the partial derivative of n with respect to x. So x here is our variable. And 2y here, derivative for this is 0 because y is assumed as constant. And derivative for negative 3x is negative 3. Again, the partial derivative of m and the partial derivative of n are equal. Therefore, this equation is exact. For our third example, 0 is equal to 2x minus y cubed dx plus y minus 3y squared x dy. As noticed, the two terms are written on one side, but that is on the right side of the equation. Nevertheless, the dx term is our first term, so this is considered as in the standard form. We will not be confused in identifying the value for m as well as the value for n. So this is our value for m. We have 2x minus y cubed. Then, for our n, that is y minus 3y squared x. Then obtain the partial derivative of m with respect to y. Y is our variable. So, derivative of negative y cubed is negative 3y squared. Again, take note our 2x is constant. For the partial derivative of n with respect to x, we have here our variable is only x. So, our n here, which is y minus 3y squared x, our first term y, derivative for this is 0 because y is assumed as constant. For the second term, I'm going to write the literal coefficients of x, or including the numerical coefficients. We have negative 3y squared. Then, get the derivative of x, which is 1. Again, the two partial derivatives are equal, so this third differential equation is exact. In our fourth differential equation, we need to write the given differential equation into a standard form. Specifically, we have to write the dy term to the left side. So I'm going to write first the dx term, 3x squared y minus 2 dx. Then, transpose dy to the left side, that is negative 5 plus x cubed dy. Then, equals to 0. From this standard form, our value for m is 3x squared y minus 2. Then our value for n is negative 5 plus x cubed. Take note, in answering this question, usually the common mistake is this sign negative. Most of the students forget to copy or to reflect the sign negative for the n term. So please be careful. You have to write the negative. Then, after this one, obtain the partial derivative of m with respect to y. So this is our m. Get the derivative with respect to y. Y here is a variable, and then I'm going to write the numerical coefficient for this y, or literal coefficients, 3x squared. Then get the derivative of y, that is 1. And derivative for negative 2 is 0. Then, for our n, get now the derivative of n with respect to x. And we will just remove the parentheses here for easy solution. So we have here negative 5, then minus x cubed. Since this is with respect to x, our x is a variable. And the derivative of negative x cubed is negative 3x squared. As shown, our two partial derivatives are not equal, therefore, this is not exact. And take note, the 2 differs only by the sign negative. If you just forget to write or to reflect the negative in our value for n, this partial derivative of n with respect to x, you will have a positive value. So you will also get mistake to conclude that this is exact, although it is not. Then the other possible mistake also, you will forget to transpose these dy terms to the left side, or you forget to write the equation into the standard form. In doing that, our sign here for our n is positive, so eventually, if we are going to write our sign for n that is positive, our partial derivative of n with respect to x is also positive, so you will also get mistake. Our fifth differential equation is written similarly with our fourth differential equation. Specifically, in both equations, the dx term is at the left side while the dy term is at the right side. The typical solution is to write the dx and dy terms at the left side, just like what we did in our fourth differential equation. However, in this fifth solution, we are going to write the dx and dy terms at the right side. We choose the right side to know the possible outcome of choosing the right side. Nevertheless, writing the equation at the right side is still in the standard form as long as the dx term is our first term. So, I'm now going to transpose the dx term to the right side. We have here 3x squared y plus y squared dx, and take note the sign here is negative, then plus x cubed plus 2xy dy. As shown, the dx term has a sign of negative. In this case, we have two options. Our first option is to retain the sign. Our second option is to multiply the equation by negative so that the dx term will become positive. In this solution, I will choose to convert the dx term into positive. So let's multiply this equation by negative 1. So we have here 0 is equivalent to 3x squared y plus y squared dx minus x cubed plus 2x y dy. From this equation, we can now proceed identifying the value for m. Our m is 3x squared y plus y squared. Then, our value for n is negative x cubed plus 2xy. Then let's remove the parentheses. So you have here negative x cubed minus 2xy. Then, let us get the partial derivative of m with respect to y. In this value for m, our y is the variable and our x is assumed as constant. Derivative for 3x squared y is 3x squared. Then derivative for y is 1. Then derivative of y squared is 2y. For the derivative of n with respect to x that is negative, take note our x here is the variable. So we have negative 3x squared, and you have the literal or numerical coefficients of x that is negative 2y. As shown, our partial derivative m and n are not equal. So this is not exact. By this time, I hope that you are already expert in identifying a differential equation, either an exact or not. So let us now proceed solving an exact differential equation. Example 4. Solve the differential equation 2xy minus 4x cubed dx plus 6y plus x squared dy equals to 0. As noticed, this equation cannot be solved with our previous methods, the separation of variables and the equations with homogeneous coefficient. So we are going to try the solution for exact equation. Our step 1 here, we are going to identify either the given equation is exact or not. From the given equations, our value for m is 2xy minus 4x cubed. Then, our value for n is 6y plus x squared. The partial derivative now for m with respect to y. That means our y is the variable. So we have here the 2x for the numerical coefficient of y. And the derivative for negative 4x cubed is 0 since x is assumed as constant. For the partial derivative of n with respect to x, the derivative for 6y is 0 and the derivative for x squared, in which x is assumed as the variable, then that is 2x. As shown, the two partial derivatives are equal, so therefore, this is an exact. For our step 2, use the formula function of xy equals the integral of m xy dx plus an unknown function of y. Let's substitute the value of m. Our m is 2xy minus 4x cubed. Then dx plus the unknown function of y. To integrate the 2xy, our x is variable while the y is constant. So to integrate this term to xy, I have to write the constant 2y. Then I have to integrate the variable x, that is x squared over 2. For our second term, negative 4x cubed, I have to write here the constant negative 4. Then integrate x cubed, that is x 4 over 4. Remember, I am just using here power formula plus the unknown function of y. Then simplify. Our function of xy is equivalent to x squared y minus x4 plus the unknown function of y. The function obtained in step 2 is almost our final answer. We are just going to add the constant c. In particular, I'm going to write here the function x squared y minus x4 plus the unknown function of y, then equate it to constant. And to solve this value for the unknown function y, we will proceed to step 3. We are going to use the given formula, that is partial derivative of f with respect to y. And I'm going to substitute the function here, f that is x squared y minus x4 plus our unknown function y, then equate it to our n value, which is 6y plus x squared. For the partial derivative of this expression, y is variable while x is constant. So the derivative for this x squared y is x squared, the constant, then derivative of y is 1. Then derivative for the constant x4 is 0 plus the derivative of that unknown function y is symbolized by this prime, then equals to 6y plus x squared. As noticed, our x squared is cancelled. Then, the partial derivative for this y is equal to 6y. To solve now the value for that unknown function of y, we will just get the integration of this equation. So integrate the left side and also integrate the right side. The answer for the left side is now the unknown function y, and in the right side is 6, and t for y is y squared over 2. Then the unknown function y is equal to 3y squared. For our step 4, we are going to substitute the value of the unknown function y to the equation obtained in step 2, that is x squared y minus x4 plus the function of y is equal to c. So we have here x squared y minus x4 plus the function of y is 3y squared is equal to c. This is our final answer. And for checking, we will just get the differential or derivative for this equation. X squared y minus x4 plus 3y squared is equal to c. The derivative for x squared y, we are going to use the product formula. That is x squared, differential or derivative of y is dy, plus y, then derivative for x squared is 2x dx. Then the derivative for negative x4 is negative 4x cubed dx. And derivative for 3y squared is plus 6y dy is equivalent now to 0. Let's simplify. X squared dy plus 2xy dx minus, I'm going to copy this third term, 4x cubed dx. Then the fourth term, 6y dy is equal to 0. Then we're going to group our dx term. We have here 2xy dx minus 4x cubed dx plus x squared dy plus 6y dy is equal to 0. Then factor the dx. We have here 2xy minus 4x cubed plus, let's factor the dy, then x squared plus 6y. And for our given problem, that is 2xy minus 4x cubed dx plus x squared plus 6y dy. Therefore, this is checked. Hello everyone, this is the end of our first video on exact equations. For the continuation, you may proceed to the second video on this topic.